right, good afternoon, everyone. Today in 2.2, we are going to graph polynomials. So the first thing we need to talk about is what is a polynomial. Okay, so polynomials, we have our n is a negative non-negative integer. So think of this: the n is going to be the exponent. And non-negative integers are whole numbers right? Because integers are positive and negative, but non-negative would just be whole numbers. 0, 1, 2, 3, 4, 5. Okay. And n is our exponent. So it's kind of in this format, which looks a little weird. Think of this: a subset n minus 1, a subset 2, a subset 1, a subset 0. Those are coefficients, okay? Those are numbers itself. But we're focusing on the exponents. The other thing to keep in mind, this is why it says n minus 1, 2, 1, and 0. Don't forget this would be x to the 0, where this is x to the first. The reason why they have that in that format is something we're going to talk about a little bit later in this section, which means we want it in standard form in order. So the first thing we're going to do is go over a couple examples of functions that we are going to determine if they're polynomials or not. So what we want to do is look at the exponents of our variables, okay? So if you look here, we have x, and we have nothing. So that's x to the 0, right? That's x to the first, and as you can see, that is x to the first. So yes, this is a polynomial, and all exponents are non-negative integers. Okay, so that's going to be, anytime we have a yes, guys, we're just going to have this explanation, so I don't have to keep writing it. Now, if it's no, we want to be specific on why. Okay, so again, I'm going to look at this x to the 0, right? Now, here I want to point out that this x here is under the square root. Well, square roots are exponents to the fraction there. So the square part is in the denominator. If it was a cube root, it would be 1/3. If it was a fourth root, it would be 1/4, so on and so on. So in this case, no, since 1/2 is not an integer. It is non-negative, but it's not an integer. Remember, integers are whole numbers. Specifically, we want the positive whole numbers. Okay, let's look at this. So we have x squared and x to the first. That's awesome. The one thing I also want to point out to you is that divided by 2, that is just a coefficient up front. So it's 1/2 x squared plus 5x. And as you can see, our exponents are non-negative integers. So yes. All right, now I'm going to use a different color because apparently my marker is not working. So again, I'm going to look at those exponents. Exponent. And look, here is our problem. We have a problem here. This is not a polynomial because our variable is in the exponent, because x is in the exponent. So that can't happen either. All right. So now if we look at this, we have to be careful at this one, because right here we have x squared. But because that's in the denominator, we actually have to change it change the way it looks so it's no denominator. We don't want x's in the denominator, and this way I can prove it to you. Because when we have them in the denominator, it actually means a negative exponent. Hopefully that sounds familiar. Happy and sad if you learned it that way. Now if we look at it, we can say no because, and of course I can't spell, because the exponent is negative. Okay, now 3, well, think of this. This is usually where our variable is, right down the end. But we have to think about this as 3 to the x to the 0. 3 times x to the 0. Anything to the 0 is 1. So that's why if this were 1, 3 times 1 is 3. So this is x to the 0. And 0 is a non-negative integer. So yes. All right, with polynomials, there's a couple of the characteristics we need to know, and we're going to be able to identify them when we see them. Right? So the degree. The degree of f is n, which is the highest variable that appears, or the highest power of the variable that appears. Then we have the leading term. The leading term is the term with the highest exponent. Okay, so in standard form, that should be the one in front, but we have to put it in standard form first. Leading coefficient is kind of that A, so it's that number in front of that leading term. And then the constant term, of course, is at the very end, and it's just a number with no variable, okay? Now, of course, that variable has the exponent of 0, so that's why it's not there. So what we're going to do here is we're going to talk about some of these, okay? Now, I want to tell you what standard form looks like. Standard form means looking at all your variables, so x, 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 and x technically, right? And you're going to put it from highest to lowest. So 5, 2, 1, and 0. So it is in order. Now we're going to state the degree, the leading term, the leading coefficient, and the constant. Okay, so of A, what is the highest exponent? That's the degree. 5. What is the leading term? 4x to the 5th. Leading coefficient. So that is looking at your leading term, and it is the number in front, which is 4. And the constant, of course, is what's added or subtracted with no variable at the very end, which in this case is -5. Okay. Now, if you see at B here, we have x to the first and then x to the third. This is not in standard form. You want to put it in standard form before you determine all of your characteristics, because then we know the leading term instead of just looking at what term was given to us first. So I'm going to put this in order, which is x to the third plus 12x. Degree, leading term, leading coefficient, and constant. So the degree is the highest exponent. What's that? 3. Leading term is, once in standard form, it's that first term there, which is x cubed. Leading coefficient. Well, leading coefficient is the number in front on that leading term. What number is there? Even though it's not showing a number, what is it? It's 1. And the constant, what is 1? What is the number without a variable? Well, there is none, and so it's 0. Okay. Now, in some cases, C and D, we have to expand it a little bit. In C, we definitely have to expand it all the way. So dividing by 5 means each part is divided by 5. So 4/5 minus 1/5 x. We still have a problem though, because it's not in standard form. So let's change this. This is negative 1/5 x plus 4/5. All right, now we have it in standard form. We can fill out our characteristics. Leading term, leading coefficient, and constant. Okay, highest degree. Do not put 0 down. This is x to the first. Leading term would be the negative 1/5 x. Leading coefficient, well, that's the number in front, negative 1/5. And what number is added or subtracted on to the end of it that has no variable? 4/5. All right, I'm going to show you D. D is not in standard form. This is actually in factored form. But I think it would be a pain and a little bit too much to be always multiplying this out, right? So let's see if we can get to our characteristics without having to multiply all of that out, okay? All right, let's talk about the degree. Now, the degree is your exponents, right? The highest exponents. Well, here's the thing. We have 2x cubed, right? Because if we cubed everything, our highest degree would be cubed here. We are still multiplying it by an x to the first and still multiplying it by an x to the first. So when we multiply, what do we do to these exponents? We add them. So our degree is 5. Now, what about our leading term? Well, I still have to do 2x cubed because there's 3 of them, right? I have to do x and I have to do 3x. Okay, this was just to find out our degree. So if I did 2x and that whole thing is cubed times x times 3x, what would we get? Don't forget to cube the 2 here. So 2 times 2 times 2 is 8. 8 times 3 is 24. And we know that it's going to be x to the 5th. Okay, because we add all those exponents. Knowing the leading term, we know our leading coefficient is 24. Now the constant, just like we multiplied all of the first terms in each of those parentheses, we can also do that by multiplying the last terms. The only thing I want you to keep in mind here is that this negative 1 is to the third. Then we have multiplied by negative 2, multiplied by 2. Okay. If this were different, some of this would change. So negative 1 times negative 1 times negative 1 is negative 1. Negative 1 times negative 2 is 2. 2 times 2 is 4. Awesome. Okay. The graph of the polynomial function will be continuous and smooth. The following graphs are not continuous and smooth. The first 2 graphs are not continuous at x equals 2, and the fourth is not smooth. Okay, so these are 4 different ways to not be continuous. You can have a hole, you can have a vertical asymptote, you can have a jump, or you can have a corner. So anytime that we get a corner here, this is not smooth. Okay, if you look at a graph, you got to think continuous would be I'm not picking up my finger, but in all of these, I'm picking up my finger to be able to trace the graph. Okay, so the intermediate value theorem. This is a theorem we're going to go through, and I'm going to explain a little bit, but then we're going to continue forward. So let me read this because it's really nice to see how the mathematical definition is and how we can interpret it with a picture. So it says, suppose f is continuous. Remember, so it goes all the way through. Suppose f is a continuous function on the interval containing x equals a and x equals b. So I'm going to draw what that statement says. So there is some sort of graph, okay, that is continuous from A to B, okay? So if this were A and this were B, we have a continuous function, okay? And of course, A is less than B. That's why I have A first, B second. If f of A and f of B have different signs, then f has at least 1 0 in between x equals A and x equals B. That is, for at least real number C, okay? C is between A and B. We have f of C equals 0. Okay. How do I explain that? Well, we know that at A, we have a value f of A. And at B, we have a value f of B. Okay. F of C, if A is less than C is less than B, then an f of C exists. This is the gist of it, okay? Because one of the biggest things why this works is because f is continuous. So if C is between A and B, so I'll just make it C, and I go up to my continuous graph, there must be an f of C that exists. This is the idea of the theorem. You work a lot more with this theorem in calculus. We're not going to worry about example 3 because we're going on to graphing polynomials, okay? So I'm going to do the long way. We know that we have zeros at 2 and -3, okay? So we know that at -3, it equals 0, and at 2, it equals 0. Okay, so we have to figure, is it going to be above the graph, below the graph, whatever we need. The long way to do this is to pick a value that's less than 2. So let's say we pick 0, since it's nice and easy. And if we pick 0, let's see, we get 9 times -2 is -18. Oh, I didn't put this in order. I made a mistake. I can't erase it. Okay, sorry guys. Put it in order. -3 and 2. Well, we know that at 0, it's -18 since I did that already. Okay, there we go. A value less than -3 is -4. So we would grab our calculator if we need to. But that would be -6. That would be -1. -1 squared is 1. So -6. And then a value greater than 2 is 3. So that's 1. And 3 plus 3 is 6. 6 squared is 36. So we're going to sketch this. I'm not going to put any y values down. I know at -4 it's under here. So I know it's going this way. I also know between -3 and 2, it's under because we're at -18 at 0. So maybe right here. So let's go down. And then you come back up. because at 3, it's going to be at 36. Okay, so our graph here looks like this. Now, of course, I'm not putting in any y values because this is a sketch. That was a lot of work. Is there a shorter way that we can do this? Well, let's talk about this. So notice, I'm going to keep this graph here. Notice what happens at the x-intercepts right here. Here we're touching. We touch and go back down, but here we cross. Is there a way in our function that we're going to be able to distinguish this without just evaluating every time? Yes, there is. If the exponent, so that's the exponent, if the exponent is even, then it touches and rebounds from where it was. If it's odd, then it crosses. So let me show you with this last example how that's going to be. The negative 3, right, to make that 0 is 2, which is even. So that's why at -3, it touched. And at 2, that exponent is 1, so that's why it crossed. Well, that's great, but can't it touch from the up and cross down here? Yes, it can. So what we also have to keep in mind is end behavior, okay? Now, so what we need to think about is this, all of the polynomial. Is it a positive polynomial? Is it a negative polynomial? And then is it odd or even? Okay, so let's remember what this is. Positive or negative have to deal with the leading coefficient, okay, leading coefficient, and then even or odd is going to be based on the degree, okay? So what I like to do when I show my students is I'll start with even, okay? So even and positive, we're up in the air like this. If it's even and negative, it flips it and we're down below. They're both going down. This is where it's going to be weird because we're reflecting each other. So I think of this as if it's odd and positive, it's almost like a disco, okay, where your left hand is down and your right hand is up. Now, if it's odd and it's negative, we flip it. So our left hand is up and our right hand is down. I think of that as a dance. So let's put everything together to see if we can sketch this out a little bit easier. All right, so first of all, let's do a table. The best way to see this is to do a table. So it's the zeros. We have 0, 2, and -3. So I'm going to put that in order. Okay. Then we're going to think of our multiplicity. Okay. So with the -3, it's a 2, so it's even. At the 0, we're cubed, so we're odd. And at the 2, our value right there is 1, so we're odd. Okay. And then we could touch or across. So remember, even is touch, odd is cross. Now, here's a little trick, how to figure out that degree. That degree is just all the multiplicities added together. So 2, 3, and 1 is 6. So this makes it an even function. Okay, and if you look right in front, it does not have a negative, so it makes it a positive function. Now, how does that help me graph? Well, the first thing I'm going to graph are my zeros. So I have a 0 at -3, I have a 0 at 0, and a 0 at 2. Then I graph my end behavior. It's an even function that's positive, so that means both my ends face up. So then I'm going to just face both my ends up. Now, because it's a sketch, I do not need my y axes, all those units there. So I'm going to go one by one. -3 is touching. So since I touch, I bounce back. If I went down here, it would cross. So at 0, so I touch and then I come back to that 0. And at 0, I cross. And then I come back up somehow. And then I get to my 2, and my 2 crosses. And what do you know? It works with my end behavior. That's why I like doing the end behavior first, because everything would fall into line if everything was right. See, the last one crosses, and if I connect that to my end behavior, it crossed. All right, so to graph a polynomial function, find the x-intercepts, the multiplicity of each intercept, find the y-intercept, determine the end behavior. This is how we get more accurate when you sketch graphs. So you guys are going to practice that in a little bit, but right now we are actually going to do some story problems. A box with no top has been fashioned from a 10-inch by 12-inch piece of cardboard. Okay, so here we go. We have this cardboard here. And it is a 10 by 12. Now, we're going to make a box, right? So what they're going to do is they cut out the corners here. And we're going to denote that as X. So we're cutting out X length here. And then we're able to fold up the sides and we have our box with no lid. Okay? So what it wants us to do is find the volume of a box as the function of X. In other words, we're going to create a function and only have X variables in it. Because think of this, volume equals length times width times height. Okay? But we don't want that. We want all X's. So if we look at this length right here, the whole thing's 10, but we're cutting out what? We're cutting out an X here and X here. So this length of our box is actually 10 minus 2X. Let's do that with the other side. This whole side is 12, but we're cutting out both X's there. So this length is actually 12 minus 2X. And that's what happens all the way around, right? All right. If we made our box and we had this 10 minus 2X by 12 minus 2X, what would be our height? So think of bending the sides of that box. What would be our height? Hopefully you said X. So when we do our volume, we have our length of 10 minus 2X times 12 minus 2X. And then we have our height of X. Now I'm going to put that on front because usually you see that on front, not back. Now we could expand this if we wanted to. And I'm going to just expand it and multiply it out for you. And I'll show you. Usually we have V of X because we're in terms of X. And it becomes, if I put this in order, it would be 4X cubed minus 44X squared plus 120X. Now, let's talk about this though, because in this problem it also says include an appropriate domain. First of all, if we talk about a box, what is the smallest volume it could be? Well, it would mean that X has to be greater than 0. It cannot equal 0 because then we don't have a box. If it was 0, we would only have two sides. We would have a flat cardboard. We would not have a box. Okay, so we know x has to be greater than 0. How do you find the greatest value that it can be? Well, what you guys do is you take the shortest side and say that that has to be greater than 0. So 10 minus 2x is greater than 0, and we're going to solve. So negative 2x greater than negative 10. Now don't forget, if we divide by a negative, we have to switch the sign, and we get 5. So the domain for this problem is that x is in between 0 and 5. And you can see this because if I put 6 in here, if I put 6 into that one, it works, right? 6 times 2 is 12, 12 minus 2 is 0. Okay, even if we put 5.5, right? We would get 11. 12 minus 11 is 1. And that's great. But again, if we put it here, 5.5, 10 minus 2 times 5.5 is a negative 1. Can we have a negative side? No. And that is why you use the shortest side to figure that out. This next problem, you will not have to do this type of question on a test because it's actually having you find the dimensions using your graphing calculator, which you know you can't use. So I'm just going to show you how to do that now. So what I'm going to do is plug in my volume equation. So x times 10 minus 2x times 12 minus 2x. I'm going to graph it. Okay. Now, I know that x has to be between 0 and 5. So 1, 2, 3, 4, 5. Let's see what I got here. Let me zoom in here just so I can do this a little bit more clear. Okay. So if I zoom, something is wrong with my equation. Did I type that in right, guys? Oh, that's why. Because what did I want? I wanted the maximum volume. There we go. I don't need the x value right now. I need the 0. I need the max value. Let me zoom out. Train of thought is gone. So, of course, according to this graph, I need the max volume. So the max is up here. So I need to move this up. Again, you're not going to have to show how to do this. Graph. I'm going to find that max. Why am I not able to do that? Okay. Let's try that again. Let's go up to 50. Okay, we're still going up there. Oh, that's why. Okay. Sorry, guys. It's taking a while. Okay, there we go. Remember, our max is where there is an increasing to decreasing. If you were to do this in the graphing calculator, we would go max. We would want to be on the left side of that max. Go over to the right side of that max. Enter, enter again. And I get that x equals 1.81 approximately. That would make my max volume this 96.77. And if I wanted to find the other two dimensions, I would just have to put the 1.81 into my two sides. Okay. If we were able to use graphing calculator, this is how you would find your maximum volume and the dimensions to each side. All right, guys, have fun doing your work.